addition as fast as you can write. There's no delay, which is like a typewriter. It's pretty cool. Yeah. The derivative of a one variable function measures its what? Oh, let's go here. Evans, what does it measure? It's rate of change. You can just say rate of change. That's fine. Yep. At a point it would. Yep, correct. So what we've chatted about this a little bit. What happens when we introduce? So when we have a two-dimensional function, we're looking at nice and safely ensconced in 2 dimensions. How many different directions can we go in, really?
4.
Well, if we're looking at, we are going 4 directions. But if I'm on this function, usually we're going left or right. We're looking at derivatives going to the right. That's what we've looked at. dy, dx, right? Going as x increases, what happens to y? What changes now when we have 2 variables? What happens? Yeah. Left and right. You could, yeah. So theoretically, exactly. So theoretically, how many different directions can we now go in? Theoretically,
4.
Yeah, we can theoretically we can go in an infinite number of directions. Theoretically. That being said, we're specifically interested in 2 directions. What directions are we looking at in this case? Yeah, we're looking at, we're going to have functions like t, and we're going to go in the x direction, and we're going to have functions, maybe, again, the same function t, and we're going to go in the y direction. So specifically when I say the x direction, x is changing. What is not changing?
Y.
Y is not changing. So we're in the y direction. What's not changing? S. So imagine you're on a mountain face. You're on a mountain. It's not just, it's some regular mountain. There's different, so at a certain point, how many different directions could you walk in? You have 360-degree rotation, right? You could walk in any given direction, right? The idea is that eventually we'll talk about any of those other directions, but for now we're specifically talking about the x direction, which would be maybe, if you're looking straight down left and right, or the y direction, which will be, the x direction might be forward and backward, and the y direction will be left and right. So the first thing we look at is just the cardinal directions, and then eventually we apply vectors and look at the other directions. Does this kind of make sense of the direction we're going in? Yeah. The tables we're now going to work with. So we have a plate, and what is this telling you? It's telling you the temperature of the plate at specific points. The temperature of the plate at specific points. So it's not uniform. Could you make a 3-dimensional graph of this? Absolutely. If you were to do a 3-dimensional graph, you'd have x, you'd have z, x and y like this, and then this coordinate system right here, it would be in the first octant because these are positive. That would be the x and y coordinate, and then you would go up to whatever the temperature is. So you get some sort of surface. We're not quite doing 3. Yeah, there might be a spike. Yeah, exactly. There's going to be a peak right here, at least in this immediate vicinity. We know nothing else about the rest of the plate. Maybe the plate continues on. The point being that if this is the temperature, we could talk about Tx at the point 2, 1. We could talk about Ty at the point 2, 1. This is the point 2, 1. Do you agree with that? Yeah. We could say 2, 1/135, but we're looking at the rates of change. So anyway, the idea is Tx is when you keep y constant. So if I asked you for what is the rate of change of x at that point if you keep y constant, which string of numbers are you really looking at? Which string of numbers, Henry? You're keeping y constant. So is the string horizontal or vertical?
Horizontal.
Yeah, you got it. Yeah, Henry, you can throw your voice pretty well. It's amazing. So look, this right here is y is constant. So we'd be looking at the rate of change around 135 left to right. But for Ty, where we keep the x value constant, we are going up and down. By far the easiest thing to mess up when you're doing these right at the beginning has nothing to do with the algebra. It has everything to do with just like misinterpreting it. So this is what I'd like you to do. On your own, without saying anything out loud, come up with your best estimate for what you think these two are right here. Do that by yourself, all by yourself.
X.
Ty is when you keep x constant, correct? So you're marching this way, right?
Yeah.
Are the numbers going up or down?
Down.
They're going down, so it should be negative. Now there's different methodologies for estimating rates of change, right? Jesse, hold on a sec. So there's different methodologies. There's basically 3 most common methods. One method is to examine the point and the next point. What's another method? The point before and that, right? Or what's another one? Go average those two, right? Go from one to the next. Or go from here to here to here and average them. So are there lots of ways to estimate rates of change? You don't have a function, so there's no definitive way to get the actual instantaneous rate of change. But it definitely should be negative. So if you do, what is it, 120 minus 155, you get what, negative 35, right? And you go from 0 to 2, so what's that going to be? Divide by 2, so you get negative 17 and a half. Generally speaking, the one I like to do the most is to do the average, like that. And then going from side to side here, you're going from 128 to 160, so you're going an increase of what?
40. That's not already.
Really? 40?
32.
I think 32 sounds better. And then you went from 1 to 3, so what do you end up at? 16. Okay. Now, I liked how you were, whoever gave me this original, Jesse, you were very good about giving me the exact units of measure. This isn't physics where I require you to write the units of measure at every single step of the way, but you do need to write them at the end. Usually on a free response question, I think you learned this last year, the units are usually like 1 point. It's part of the answer point. Like you can't get more than 1 point off, but do those 1 points add up? Yeah, only 108 points on the exam itself. So what you're going to see are these two definitions. And all it is as h goes to 0. So what this right here is the x coordinate. So this is what's changing here. The only thing that is changing is x. So what's the only thing that's changing on the next one?
Y.
Y is the only thing that's changing. Everything else is staying fixed. So if the symmetry is there, they're the same. So at let's look at point P right now. At point P, if you were on point P right there, what does it look like dz, or not dz, the partial of z with respect to x?
How do you call that?
I usually say partial. I just say partial z with respect to x. Partial. Yeah, you can do that too. It's fine. I'll understand, or I will eventually. For dz dx, and again, I will say that it's not correct, but just bear with me. Partial z with respect to x. Is that going to be positive or negative, do you think? So if with respect to x, what are you keeping constant? Y. So if you make the cut, that's what the cut looks like, right?
Well, I'm not sure about that. Which side is
Exactly. So that's exactly the point. So you're not sure. It looks like it's going to change somewhere on that plane right there, right?
Yeah.
So it looks like potentially it could be any three of it. It could be 0, right? Maybe it's at the top of that path, or maybe it's positive and maybe it's negative. When I give you questions like this, and I can guarantee you will see questions like this on quizzes and on tests, I will try to make it absolutely clear where it is. So let's move it here. If I just move P over here, what does it look like that directional derivative is going to be?
Negative.
If P is moved to there, it really looks like it's going to be negative. And then also, what does it look like dy is going to be? Partial z with respect to y is going to be negative. Exactly. So over here, what about over here? It does look like this is to the left of the xz plane. So for Q, and this is at point P, right? Partial z with respect to x at point Q. So partial z with respect to x at point Q, let me draw that correctly. Does it look like it's positive or negative? Partial z with respect to x. So you're holding y constant, right? What's it going to be? What do we think? Partial z with respect to x. Again, is this kind of ambiguous? Is it again in the kind of a slightly ambiguous spot? It's really hard to see, even if I zoom in, right? Because look what happens if this was on that exact arc, if it was on the xz plane. So this is the xz plane, right? Right here. Right there, I'm holding y constant, right? So that would be dx, right? So it's x. So it does look like, though, which direction is it? It looks like it's going down, right? It's going down. So it does look. If let's assume it was on it, okay? But then what about dy right here? If we hold x constant, it looks. If I told you it was on the xz plane, let's say I said it was on the xz plane, you would say, assuming it is, partial z with respect to q is going to be, not q, sorry, dy at q is going to be what?
0.
If we assume it's on that plane. Now that would be a way I could specify. I could be like, this is a inverted parabola facing down. The point, it's around the origin. The point is on that plane. You'd have to understand what's being written, and you'd also have to kind of see what it looks like.